Hi, this is Tim DeStasio, and this is Psychrometrics for HVAC Technicians, Part 3. As a reminder, this training series is designed for HVAC technicians, not so much for engineers or designers, but really service technicians that run service calls on comfort and humidity problems and need to understand the basics and the practical knowledge of psychrometrics. In this training module, we'll talk about wet bulb temperature and how to use it to charge refrigerant properly into a system. We'll talk about how to diagnose cooling problems looking at supply and return wet bulb temperature. As a review, if you know two properties of air, you can plot an operating point on the Psych chart. For example, our dry bulb temperature is measured by a normal thermometer. Doesn't take into account, though, the heat that's in the moisture in the air. So if you see here, we're plotting 75-degree dry bulb on our Psych chart. Now, relative humidity measures the moisture in the air that's compared with the total amount of moisture that the air can hold at that temperature, at that dry bulb temperature. So a relative humidity curve may look like this. In this case, our air temperature is 75-degree dry bulb, and it's 60% relative humidity. Where those two lines cross, that's our operating point. And a process happens anytime that the air properties change. So we can heat air, we can cool air, we can dehumidify air. Anytime we change the properties of air, that's called a process. And the air conditioning process cools the air past its dew point, thus dehumidifying the air. So it kind of looks like this. We start off with our return air, it passes through the evaporator coil, it gets cooled and dehumidified. And that process, you can connect those 2 points there with a line, and that's called your process line. So wet bulb temperature, it takes into account the heat that's present in the moisture of the air, therefore a better picture of how much total heat is in the air. Now, there are different devices that are meant to read wet bulb temperature. One is called a psychrometer, and another is called a hygrometer. Both of them read dry and wet bulb temperature, but the hygrometer, especially if it's an electronic device, can convert those numbers, and now we can know what our relative humidity is, our dew point, our grains, and other properties of the air. All because we know the two original properties, which is dry bulb temperature and wet bulb temperature. And here's an example of a hygrometer. This is a smart probe made by Fieldpiece. Many technicians use it. This can be placed in the airstream and read not only the dry bulb, but also the wet bulb temperature. And from there, other properties can be derived. Wet bulb temperature measures the evaporative cooling effect of the air based on how much moisture is already in the air. So to better understand that, we should probably look at the old sling psychrometer. This was an early tool that was used by technicians for many years, up until more accurate electronic devices came out. And it's really comprised of a normal thermometer that is covered by a wet cotton wick. So here we see a picture of an old sling psychrometer. If you notice to the left of this picture here, there are 2 thermometers. The thermometer on the left over the bulb is covered with a wet cotton wick. This is your wet bulb thermometer. And then your dry bulb thermometer is right next to it, which is just a normal thermometer. And the technician would start slinging that in the air and sampling the air. And as the temperature starts dropping and coming off of the wet bulb thermometer, this happens because there's an evaporative cooling effect that takes place when that moisture from the wick starts leaving the wick and gets absorbed in the air around it. And this is really what happens. You notice on the left, you've got your dry bulb thermometer that's simply reading the air temperature, but your wet bulb thermometer has that wet cotton wick. And as that moisture leaves the wick and gets evaporated into the air around it, there's a cooling effect that takes place, and the temperature of that thermometer drops. And that is your wet bulb temperature. So as moisture evaporates from the wick, it creates a cooling effect that we call wet bulb temperature. And this is important to know because equipment charging charts use wet bulb temperature as well as dry bulb temperature. So it's not enough for us simply to be able to read one or the other. We need to be able to read both. The effects of humidity on wet bulb temperature. Here's something that most of us know. Moisture travels from wet to dry. So in the case of a wet bulb thermometer, we've got a lot of moisture in that wick, and it's going to travel from that wet wick into the air that's not as wet. It's drier than the wick. And so that's the direction that moisture will travel. Now, if the air around the wick is close to its saturation point, so it's very humid air, there'll be very little moisture transfer because the air cannot absorb much more moisture than what it already has. And so wet bulb and dry bulb temperatures will be very close to one another. But if the air is dry or less humid, the air around it is farther away from its saturation point, there is more moisture to absorb off that wick into the air, and your wet bulb and your dry bulb temperature will start separating from each other. And we're going to start feeling cooler because our wet bulb temperature is cooler. And our bodies really react more to wet bulb temperature than they do dry bulb temperatures, we'll see. The lower the wet bulb temperature is, the less heat is in the air. And so we feel cooler. Notice this runner in the slide here. He's pouring water on his head. Now, that water didn't come out of a refrigerator. It's the same temperature as the air around him because it's probably been sitting on a table all day. But why does he feel cooler when he pours that water on his head? And why does he continue to feel cooler for a long time after he's done that? That's because his hair has absorbed that water. And as that water evaporates back into the air around him, that evaporative cooling process cools him down. Now, if it's a very humid day, there's not going to be as much evaporative cooling, and so he's not going to feel as cool. But if it's a drier day, there's going to be a lot of evaporative cooling that takes place because the outdoor wet bulb temperature is a lot lower, and he's going to feel very cool and refreshed after doing that. How do we plot wet bulb on the Psych chart? Well, we use the same scale as the dew point. So notice here on the left side, that saturation curve there, those blue numbers, those are the same numbers that we use for dew point. But the difference is, instead of drawing a horizontal line to get to that scale, we're going to draw a diagonal line to get to that scale, just like this. So our wet bulb lines are diagonal lines. Don't get that confused with dew point, which would be horizontal lines. So let's do an exercise. We're going to solve for wet bulb by looking at two other properties of the air. We've got 75-degree dry bulb, 40% relative humidity. So here's our 75 dry, here's our 40% RH, here's our operating point. What is our wet bulb temperature? We're going to take this operating point, we're going to draw a diagonal line until we hit our wet bulb scale. And in this case, it's 59.6 degrees wet bulb. And it's very important for us to be able to be as accurate as we can with wet bulb temperature. We need to, instead of rounding to the nearest whole number, we really need to take it at least 1/10 of a degree to be as accurate as possible. So instead of rounding to 60-degree wet bulb, we're going to say this is 59.6 degree wet bulb. From there, we can solve for dew point, which is 50 degrees. We can solve for grains, which is 54. Return air wet bulb and coil load. Wet bulb temperature has a huge effect on the amount of heat load that the evaporator coil sees. And so, for example, in arid climates like Arizona, you may have a higher dry bulb temperature that hits that evaporator, but lower wet bulb temperature. For example, Phoenix, Arizona, if we're looking at outdoor design conditions, it may be 100 degrees outside in Phoenix, Arizona, but notice that our wet bulb is only 69 degrees. Now, let's compare that with a more humid climate. Humid climates may have a lower dry bulb temperature, but higher wet bulb. And so Charlotte, North Carolina, which is close to where I live, the typical outdoor design conditions in the middle of summertime is going to be 90 degrees, not 100, but 90. So it's cooler outside than Phoenix, Arizona, but the wet bulb conditions are a lot higher, 74-degree wet bulb. So which one has more heat in the air? It's the one with the higher wet bulb temperature, and it's not Phoenix, Arizona. It's actually Charlotte, North Carolina that has more heat in the air. And this has to be accounted for when we're charging the system. Wet bulb temperature is a better indicator of true load than dry bulb temperature, and that's why we see wet bulb temperature on a typical charging chart instead of just dry bulb. So let's take a look at that charging chart. Notice this charging chart only asks for two things. It asks for your return air wet bulb and your outdoor dry bulb temperature. So we're going to be charging the system first in Phoenix, Arizona. Our outdoor dry bulb conditions are 100 degrees outside and 60-degree wet bulb indoors. What is our target superheat? It's only 3 degrees. Now let's take that same exact unit and pluck it out of Phoenix, Arizona, and drop it in Charlotte, North Carolina, where the conditions there are 90 degrees dry bulb outside temperature, but 65-degree wet bulb indoors. So it's much higher wet bulb temperature indoors because there's more humidity in the air. What is our target superheat then? Now it's 10 degrees. So do you see that it's very important for us to be able to read wet bulb temperature when we're charging a unit, because that greatly affects how much refrigerant we're going to put in that system. It's also important for us to be able to read and understand wet bulb temperature on the supply side as well. During the air conditioning process, the evaporator cools down the air. It cools it down past its dew point. Water starts falling out of the air in the form of condensate, and the air is now cooler and less humid. So it cools and dehumidifies that air, and then it supplies it back into the room where it mixes with the air in the room, and it brings the room conditions down. So the goal of air conditioning is really to lower not only our dry bulb temperature, but also our wet bulb temperature. So let's do an exercise. 75-degree dry bulb is in a return air and 65 wet bulb. When we plot that, here's our operating point. Now let's see what our supply air temperature is doing. That's 50-degree dry, 50-degree wet bulb temperature. So that's right here. Notice how that air is at its saturation point. It's resting on that saturation curve. Our dry bulb, wet bulb, and dew point are all the same temperature. That's because our air has been cooled down to its dew point. And this would happen in a perfect world where all three of these numbers, our dry bulb, wet bulb, and dew point, are all the same. But in reality, some of that air is not going to come in contact with a coil. Believe it or not, it's going to get through the fins and the tubes in that coil, and it's going to remain untouched. And this is called bypass factor. So in reality, when we measure air coming off an evaporator coil, we're actually going to be reading it more like here, where you see on the chart now. See, it's slightly off the saturation curve. It's slightly warmer because some of that air never came in contact with a coil. So in reality, this is really what you're probably going to be reading in the field. Around 55-degree dry bulb, 53 degrees wet bulb supply air. This is kind of what our target is, what we want to see. So once again, we lower the room wet bulb temperature by delivering very low wet bulb and dry bulb temperature air to the room via the supply ducts. That very low temperature air mixes with the air in the room, and the room cools down. Now, let's troubleshoot some problems with supply air wet bulb. Again, the AC process cools the air down below its dew point. So here's our operating point for our return. Our supply air temperature difference, if we're looking just simply at dry bulb, is normally 15 to 25 degrees split, right? So that would look like something like this. So notice in this case that our wet bulb and our dry bulb are very close to each other. They're less than 3 degrees apart. That's what you want to see. Wet bulb and dry bulb need to be very close to each other. They may not be exactly the same temperature, but they need to be within 3 degrees of each other for the system to be acting properly. Now, let's plot this in Measure Quick. If you notice these conditions here, Measure Quick is happy. But if we start seeing conditions where a dry bulb temperature is below 15 degrees split, and our wet bulb temperature and our dry bulb on the supply air are more than 3 degrees apart, this generally means there's a cooling problem. Let's see what that looks like on the Psych chart. So instead of being here, it's really going to be here. Now, if you notice, we didn't cool the air down as much. And now our dry bulb and wet bulb temperature are more than 3 degrees apart, and we may have a problem. So what could be the cause? Well, let's run one scenario. It's a starved evaporator coil. This can be caused by an undercharged system or an underfeeding metering device. Maybe you have a liquid line restriction, anything that's going to starve the evaporator coil of liquid refrigerant. It's going to underfeed that coil. And we're going to see a scenario like what we're seeing here on this chart. If it's slightly underfed, the dry bulb and the wet bulb will be somewhat close to each other. still within 15 degrees, but notice that dry bulb temperature drop, only 15-degree drop. Now you may see these conditions. You got a 15-degree drop, you got 65-degree dry bulb. Your wet bulb is maybe not 3 degrees apart, but it's 4, it's 61-degree wet bulb. You may see these conditions and you may walk away thinking that the unit is working good. But notice something here. Notice what our incoming grains of moisture was. It's 78 grains, right? But notice what our supply air grains is. It's only 74. We didn't really dehumidify that air much. We didn't really remove a lot of heat. And so causes of a starved evaporator might be a low charge, a failed metering device, a liquid line restriction. Any of those things are going to cause what we see here. And as you can see, this is not acceptable. Measure Quick is not happy. There in the upper right, it's got a red flag. That's not something we want to walk away from. Let's take a look at another scenario. This time we have supply air heat gain. Now notice what you see here. You've got in your supply side, of course, our return air temperature conditions are the same as the last problem. But then in this slide, we've still got 65-degree dry bulb temperature. So that's the same as what we had with the starved evaporator. Both cases, you had 65-degree dry bulb. But in this case, notice how our wet bulb temperature is still pretty low. It's 55 degrees. Whereas with the starved evaporator, we had a much higher wet bulb at 61. So what could be happening here? Well, you could have a system that is cooling properly, but the supply air could be gaining heat after the evaporator. You're still going to have a comfort problem, but you're going to be able to tell what the difference is by looking at your supply wet bulb and dry bulb temperatures. So what could cause this? Well, you could be running poorly insulated ducts through a hot space like an attic in the middle of summertime, or you could have an electric strip heat that's stuck on. Anything that's going to cause the air after it leaves the evaporator to start picking up heat is what we call supply air heat gain problem, and that causes service calls. So notice here, Measure Quick, it's not happy. We have a red flag. If dry bulb, though, is measured without wet bulb, it could be diagnosed as something completely different. You could be thinking you're low on refrigerant. Maybe you have a bad TXV or a liquid line restriction, because in both cases, you're reading 65-degree dry bulb. So do you see now why it's important to read wet bulb in addition? Because that's going to help narrow down the problem a lot better. So the difference between this problem and the last problem is our wet bulb temperature. In this case, our wet bulb is still pretty low. It's 55 degrees, whereas the last case, it was a lot warmer wet bulb. But there's a big separation between our dry bulb and wet bulb temperature. Remember, we're looking for less than 3 degrees between supply dry bulb and wet bulb temperature. And here we have 10 degrees. So something is way off. Look how far we are away from the saturation curve. That air is not being delivered to the room at a low temperature or anywhere close to its saturation temperature. So we still have a problem here. And also look at our grains of moisture. We did actually remove a lot of moisture from the air this way, but we still have cooling problems. But you notice a difference between this problem and the last one. Our equipment actually cooled the air down. It did its job, but then the air picked up heat after it left the equipment. So it more did something like this. Notice what happens with our return air operating point as our air starts to cool down. Our evaporator did cool and dehumidify the air, then the air picked up heat. Let's see that animation again. We cooled our air down to our saturation curve, but then it picked up heat. And this is what happens when you have supply air heat gain. So the equipment capacity seemed okay, but our delivered capacity to the room was actually insufficient. And this can be confirmed by moving our probe from the supply register to the equipment. And so this will help you to diagnose where you're picking up your heat. You always want to read your supply air coming out of the vents because this is your delivered capacity. But sometimes if that air is picking up a bunch of heat, then you should move that probe to the supply plenum to see whether you're still picking up heat or not. If you move it to the supply plenum, this air has not had the effects of ducts in a hot space, so you should see something a lot different there. If you still see a huge separation between dry bulb and wet bulb temperature, maybe you have a heat strip that's stuck on and you're still reading that heat being picked up in the supply plenum. So moving your probe around is going to help you diagnose those problems. And trust me, a system that's operating like this is not going to effectively cool a room. As you can see, Measure Quick, they're in the top right. There's a red flag there. It wants you to look into it further. So this brings us to a review. Wet bulb temperature measures the heat in the air, which contains moisture. The more moisture that's in the air, the higher the wet bulb temperature and the less comfortable that we feel. And it's very important for us to be able to measure return wet bulb, because that's what we need to use a charging chart. And when we're charging charging refrigerant into a system, especially a fixed orifice system. We also need to be able to measure supply wet bulb to diagnose comfort problems. Our supply wet bulb and dry bulb should be within 3 degrees of each other for most comfort cooling situations. If we have a scenario where we have a high supply wet bulb and a high supply dry bulb, this indicates an inefficient evaporator. We may be low on charge. We may have a bad metering device. We may have a liquid line restriction. Our evaporator is not getting cold enough. But if we have a scenario where we have a low supply wet bulb, but a high supply dry bulb, this could indicate possible heat gain after the evaporator. Our ducts could be running through a hot space. They don't have enough insulation. We may have some kind of heat strip or other reheat that's warming that air up after the evaporator. We may not exactly have an equipment problem. We may have a problem after equipment. And being able to measure that is going to help you diagnose that properly. So in the next module, we're going to talk about sensible heat, latent heat, and total heat. We'll also talk about how to convert total heat into enthalpy, and the enthalpy, the formula, the total heat formula, which helps us to understand how much heat is either being added or removed from a space. So you've got a 3-ton unit. It's not keeping up. Is it a unit that's undersized, or is it a unit that's not working properly? That's what we'll talk about in our next module, and we'll troubleshoot comfort problems with enthalpy. So as always, I hope you learned something here. Thank you for watching. Leave some questions and comments below, and as always, stay safe.